So this is a very interesting problem from RMO 2009, and it sort of depends on a very simple observation about lengths. Now let's quickly see what that is. Suppose if you have any triangle ABC, and let's pick a point D on the side BC and join AD. So question is, what can we say about AD, about the length of AD? Now, one of the simplest things that we can say is AD is less than or equal to at least one of the two sides containing it. So let's suppose we write the maximum of AB and AC. So if you look at the larger of the two sides, AB and AC, and pick that up, AD is guaranteed to be smaller than that. Now why is that? Why is this true? And that depends on actually a very simple observation again. If you look at these two angles, one is theta, one is 180 degree minus theta. One of these two angles is 90 degree or more, right? Because if both of them are less than 90 degree, their sum will be less than 180 degree, which of course doesn't make sense. It's a straight line. This angle must be 180 degree. So one of theta or 180 degree minus theta must exceed 90 degree. I mean, or both could be equal to 90 degree. Both could be equal to 90 degree. In that case, AD will be perpendicular. Anyway, so suppose if theta is greater than or equal to 90 degree, as it is in this picture, then in the triangle ABD, theta is the largest angle, because if a particular triangle has an angle which is larger than or equal to 90 degree, that angle got to be the largest one, right? So theta is the largest angle. And we know, and this is a very easily proven fact, that side opposite to the largest angle is largest. So in this particular triangle, in the case that we have drawn it, AB will exceed any other side of this particular triangle. In particular, it will be exceeding the length of AD. So AB will be greater than or equal to AD. Well, if it's 90 degree, it will be actually strictly greater than. Okay, so this property, and in fact this strictly greater than, less than, can be extended here as well. Not equal to, so it will be strictly less than the maximum of the two sides. Anyway, so the point is this, that if we draw a line, and this is intuitively, you should remember this, if we draw a line inside a triangle, and that line will be smaller than at least one of the two lines containing that particular particular length, AD in this case. So if you understand this proof, then we can come back to this problem, which is from RMO 2009. It says that we have a convex polygon G such that distance between any two vertices of G does not exceed 1. So of course we cannot draw any convex polygon. So what I'll draw is I'll just draw some of the sides of the polygon. So this is, and there could be more sides here, more sides here. What the statement of the problem says is that the distance between any 2 points, any two vertices of G does not exceed 1. So even if you join these two, for example, or these two, the distance between them does not exceed 1. So let me not draw those. Let's keep it a little bit neat. Now what we need to show is that even if you do not choose points on the vertices, if you choose random points on the boundary and then join them, even then, suppose this is A, this is B, then AB will be less than or equal to 1. That's what we want to show. So the distance between any 2 points on the boundary of G, so A and B suppose, that does not exceed 1. Okay, how can we show this? We can easily show this by the problem that we just did a few minutes back. Join these two sides. Suppose this is R, this is S. Then AB is smaller than one of these two sides, right? BR or BS. So suppose AB is smaller than BS. Without loss of generality, we can assume that BS is larger, at least in this picture it is. Otherwise it will be larger than the larger of the two sides of BS and BR. So suppose AB is smaller than BS, join these two, T and M. So again, BS is smaller than ST and SM. I mean the larger of these two, so max of these two, by the same previous property that we discussed. So BS is smaller than the larger of ST and SM. So suppose it is SM. Again, without loss of generality, we can suppose that BS is smaller than SM. And finally, we know that SM is connecting two vertices of this polygon. So SM has to be less than or equal to 1, right? So SM is less than or equal to 1. So SM is less than or equal to 1. So we have the final result now. We have AB less than BS less than SM, which is less than or equal to 1. So clearly the length AB is smaller than 1. That's what they wanted us to show in the first part. In the second part, that's also pretty simple. Once we know the first lemma, that if x and y are two distinct points inside G, prove that there exists a point Z on the boundary of G such that xz plus yz is less than or equal to 1. So maybe I can draw the picture one more time. Suppose we have this polygon one more time, and I can draw a little bit more. So we have two points inside the maybe a little bit differently. So maybe like this, x and y. There are 2 points inside the polygon, and we are searching for. So goal is find a point Z on the boundary. Find a point Z on the boundary such that xz plus yz is less than or equal to 1. So the key idea is extend xy in both directions, and let's call this one as z1 and this one as z2. So what we will do is we will pick the smaller one. That means smaller one amongst xz2 and yz1. So look at the length of yz1 and xz2, whichever one is smaller. So in our picture xz2 is smaller, and we will call that particular point. So we'll choose z2 as our z. So choose z2 as z, and it will work. Why will it work? The reason is this, that xz2 plus yz2, we want to show that this is less than or equal to 1. So yz2 can be written as yx plus xz2, right? Yx plus xz2, that is yz2. So this is xz2 plus yx plus xz2. Now notice that we picked the smaller one. Xz2 was smaller than yz1. Xz2 was smaller than yz1. So if I replace xz2, if I replace that by yz1, I'll get something larger, right? I'm replacing xz2 by something larger. So xz2 plus yx plus yz1, that is larger than the previous thing. It could be equal if xz2 and yz1 are equal, then obviously this will be equal. Otherwise it will be larger. And this is just z1, z2. This is simply z1, z2. And previously we showed that z1, z2, or any 2 points connecting the any segment connecting points on the boundary does not exceed 1. So clearly this z1, z2 does not exceed 1 because it connects 2 points on the boundary. So we showed that xz2 plus yz2 has to be less than or equal to 1 as desired. Thank you for watching and keep doing great problems.